Chapter 3. Kinetic Theory of Gases and Radiation. Exercises pages 73 to 74. Exercises Q1.1, page 73. Choose the correct option. In an ideal gas, the molecules possess 1. Only kinetic energy 2. Both kinetic energy and potential energy 3. Only potential energy 4. Neither kinetic energy nor potential energy. Solution. Only kinetic energy. Exercises Q1.2, page 73. Choose the correct option. The mean free path lambda of molecules is given by where n is the number of molecules per unit volume and d is the diameter of the molecules. Exercises Q1.3, page 73. Choose the correct option. If the pressure of an ideal gas decreases by 10% isothermally, then its volume will underscore 1. Decrease by 9% 2. Increase by 9% 3. Decrease by 10% 4. Increase by 11.11%. Solution. Exercises Q1.4, page 73. Choose the correct option. If A equals 0.72 and R equals 0.24, then the value of trail is 1. 0.022. 0.043. 0.44. 0.2. Solution. 0.04. Exercises Q1.5, page 73. Choose the correct option. The ratio of emissive power of perfect blackbody at 1327 degrees Celsius and 527 degrees Celsius is 1. 4. 1 2. 16. 1 3. 2. 1 4. 8. 1. Solution. 16. 1. Exercises Q2.1, page 73. Answer in brief. What will happen to the mean square speed of the molecules of a gas if the temperature of the gas increases? Solution. If the temperature of a gas increases, the mean square speed of the molecules of the gas will increase in the same proportion. Exercises Q2.2, page 73. Answer in brief. On what factors do the degrees of freedom depend? Solution. The degrees of freedom depends upon I, the number of atoms forming a molecule, E, the structure of the molecule, E, the temperature of the gas. Exercises Q2.3, page 73. Answer in brief. Write ideal gas equation for a mass of 7 grams of nitrogen gas. Solution. Exercises Q2.4, page 73. If the density of oxygen is 1.44 kilograms per cubic meter at a pressure of 105 nm2, find the root mean square velocity of oxygen molecules. Solution. Exercises Q2.5, page 73. Answer in brief. Define athermanous substances and diathermanous substances. Solution. Athermanous substances. Substances that don't allow transmission of infrared radiation through them are called athermanous substances. For example, wood, metal, CO2, water vapors, etc. Diathermanous substances. Substances that allow transmission of infrared radiation through them are called diathermanous substances. For example, rock salt, pure air, glass, etc. Exercises Q3, page 73. When a gas is heated, its temperature increases. Explain this phenomenon on the basis of the kinetic theory of gases. Solution. Molecules of a gas are in a state of continuous random motion. They possess kinetic energy. When a gas is heated, there is an increase in the average kinetic energy per molecule of the gas. Hence, its temperature increases, the average kinetic energy per molecule being proportional to the absolute temperature of the gas. Exercises Q4, page 73 explain, on the basis of the kinetic theory of gases, how the pressure of a gas changes if its volume is reduced at a constant temperature. Solution. The average kinetic energy per molecule of a gas is constant at a constant temperature. When the volume of a gas is reduced at a constant temperature, the number of collisions of gas molecules per unit time with the walls of the container increases. This increases the momentum transferred per unit time per unit area, i.e., the force exerted by the gas on the walls. Hence, the pressure of the gas increases. Exercises Q5, page 73. Answer in brief. Mention the conditions under which a real gas obeys ideal gas equation. Solution. A real gas obeys the ideal gas equation when the temperature is very high and pressure is very low. Note, under these conditions, the density of a gas is very low. Hence, the molecules, on average, are far away from each other. The intermolecular forces are then not of much consequence. Exercises Q6, page 73. Answer in brief. State the law of equipartition of energy and hence calculate the molar specific heat of monatomic and diatomic gases at constant volume and constant pressure. Solution. Law of equipartition of energy states that for a dynamical system in thermal equilibrium the total energy of the system is shared equally by all the degrees of freedom. The energy associated with each degree of freedom per molecule is 1/2 kBt, where Kb is the Boltzmann's constant. For example, for a monoatomic molecule, each molecule has 3 degrees of freedom. According to kinetic theory of gases, the mean kinetic energy of a molecule is 3/2 kBt. A soft or non-rigid diatomic molecule has, in addition, 1 frequency of vibration which contributes 2 quadratic terms to the energy. Hence, the energy per molecule of a soft diatomic molecule is. Exercises Q7, page 73. Answer in brief. What is a perfect blackbody? How can it be realized in practice? Solution. A perfect blackbody or simply a blackbody is defined as a body which absorbs all the radiant energy incident on it. Ferri designed a spherical blackbody which consists of a hollow double-walled, metallic sphere provided with a tiny hole or aperture on one side, Fig. The inside wall of the sphere is blackened with lampblack while the outside is silver-plated. The space between the two walls is evacuated to minimize heat loss by conduction and convection. Any radiation entering the sphere through the aperture suffers multiple reflections where about 97% of it is absorbed in each incidence by the coating of lampblack. The radiation is almost completely absorbed after a number of internal reflections. A conical projection on the inside wall opposite the hole minimizes the probability of incident radiation escaping out. When the sphere is placed in a bath of suitable fused salts, so as to maintain it at the desired temperature, the hole serves as a source of blackbody radiation. The intensity and the nature of the radiation depend only on the temperature of the walls. A blackbody, by definition, has a coefficient of absorption equal to 1. Hence, its coefficient of reflection and coefficient of transmission are both 0. The radiation from a blackbody, called blackbody radiation, covers the entire range of the electromagnetic spectrum. Hence, a blackbody is called a full radiator. Exercises Q8.1, page 73. Answer in brief. State the Stefan-Boltzmann law. Solution. The Stefan-Boltzmann law describes the power radiated from a blackbody in terms of its temperature. Specifically, the Stefan-Boltzmann law states that the total energy radiated per unit surface area of a black body across all wavelengths per unit time is directly proportional to the fourth power of the black body's thermodynamic temperature T. J equals sigma T4. Where sigma equals 5.670373 times 10 to 8 Wm2K4, Stefan-Boltzmann constant. Exercises Q8.2, page 73. Answer in brief. State the Wien's displacement law. Solution. According to Wien's displacement law, as the temperature of a black body rises, the peak of the distribution curve shifts towards the shorter wavelength lambda. Thus, lambda mount equals b, a constant, where b equals 2.898 times 10 minus 3 mK. Exercises Q9, page 73. Answer in brief. Explain the spectral distribution of blackbody radiation. Solution. All objects with a temperature above absolute 0, 0 K, minus 273.15 degrees Celsius emit energy in the form of electromagnetic radiation. A black body is a theoretical or model body that absorbs all radiation falling on it, reflecting or transmitting none. It is a hypothetical object which is a perfect absorber and a perfect emitter of radiation over all wavelengths. The spectral distribution of the thermal energy radiated by a blackbody, i.e. the pattern of the intensity of the radiation over a range of wavelengths or frequencies, depends only on its temperature. The characteristics of blackbody radiation can be described in terms of several laws. 1. Planck's law of blackbody radiation, a formula to determine the spectral energy density of the emission at each wavelength, E lambda, at a particular absolute temperature T. In the image above, notice that the blackbody radiation curves have quite a complex shape described by Planck's law. The spectral profile, or curve, at a specific temperature corresponds to a specific peak wavelength, and vice versa. As the temperature of the blackbody increases, the peak wavelength decreases, Wien's law. The intensity, or flux, at all wavelengths increases as the temperature of the blackbody increases. The total energy being radiated, the area under the curve, increases rapidly as the temperature increases, Stefan-Boltzmann law. Although the intensity may be very low at very short or long wavelengths, at any temperature above absolute zero energy is theoretically emitted at all wavelengths. The blackbody radiation curves never reach zero. Exercises Q10, page 73. Prove Kirchhoff's law of radiation theoretically. Solution. Consider an ordinary body O and perfectly black body B of the same dimension suspended in a uniform temperature enclosure as shown in the figure. At thermal equilibrium, both the bodies will have the same temperature as that of the enclosure. Let E equals emissive power of ordinary body O, E flat equals emissive power of perfectly black body B, A equals coefficient of absorption of O, E equals emissivity of O, Q equals radiant energy incident per unit time per unit area on each body. Quantity of heat absorbed per unit area per unit time by body O equals AQ. Quantity of heat energy emitted per unit area per unit time by body O equals E. Since there is no change in temperature, E equals AQ. Q equals E, A. 1. Quantity of heat absorbed per unit area per unit time by a perfectly black body, B equals Q. The radiant heat energy emitted per unit time per unit area by a perfectly black body, B equals E flat since there is no change in temperature. E flat equals Q. 2. From equations 1 and 2. Exercises Q11, page 73. Calculate the ratio of the mean square speeds of molecules of a gas at 30 K and 120 K. Solution. Exercises Q12, page 73. Two vessels A and B are filled with the same gas where the volume, temperature, and pressure in vessel A is twice the volume, temperature, and pressure in vessel B. Calculate the ratio of the number of molecules of the gas in vessel A to that in vessel B. Solution. Exercises Q13, page 73. Answer in brief. A gas in a cylinder is at pressure P if the masses of all the molecules are made 1/3 of their original value and their speeds are doubled, then find the resultant pressure. Solution. M2 equals M1/3. VRMS2 equals 2 VRMS1 as the speeds of all molecules are doubled. Exercises Q14, page 74. Answer in brief. Show that RMS velocity of an oxygen molecule is square root 2 times that of a sulfur dioxide molecule at STP. Solution. Exercises Q15, page 74. Answer in brief. At what temperature will oxygen molecules have same RMS speed as helium molecules at STP? Molecular masses of oxygen and helium are 32 and 4 respectively. Solution. Exercises Q16, page 74. Answer in brief. Compare the RMS speed of hydrogen molecules at 127 C with RMS speed of oxygen molecules at 27 C given that molecular masses of hydrogen and oxygen are 2 and 32 respectively. Solution. Exercises Q17, page 74. Find the kinetic energy of 5 liters of a gas at STP, given the standard pressure is 1.013 times 105 nm2. Solution. Exercises Q18, page 74. Calculate the average molecular kinetic energy I per kilomole E per kilogram E per molecule of oxygen at 127 degrees Celsius, given that the molecular weight of oxygen is 32, R is 8.31 J mole minus 1 K1 and Avogadro's number Na is 6.02 times 1023 molecules mole minus 1. Solution. Data. T equals 273 plus 127 equals 400 K. Molecular weight equals 32, therefore molar mass equals 32 kilograms per kilomole. R equals 8.31 J mol 1 K1. Na equals 6.02 times 1023 molecules mole minus 1. I. The average molecular kinetic energy per kilomole of oxygen equals the average kinetic energy per mole of oxygen times 1000. Exercises Q19, page 74. Calculate the energy radiated in 1 minute by a blackbody of surface area 100 square centimeters when it is maintained at 227 degrees Celsius. Given. Sigma equals 5.67 times 10 to 8 with M2. K4. Solution. Data. T equals 1 minute equals 60 s, A equals 100 square centimeters. Equals 100 times 10 to 4 M2 equals 10 to 2 M2, T equals 273 plus 227 equals 500 K, sigma equals 5.67 times 10 to 8 with M2. K4. The energy radiated, Q equals sigma AT4T, equals 5.67 times 10 to 8, 10 to 2, 504, 60 J. Equals 5.67, 625, 60, 10 to 2, J equals 2126 J. Exercises Q20, page 74. Energy is emitted from a hole in an electric furnace at the rate of 20 W when the temperature of the furnace is 727 degrees Celsius. What is the area of the hole? Take Stefan's constant sigma to be 5.7 times 10 to 8 JS1 M2K4. Solution. Exercises Q21, page 74. The emissive power of a sphere of area 0.02 square meters is 0.5 kilocalories S-1 M2. What is the amount of heat radiated by the spherical surface in 20 seconds? Solution. Data. R equals 0.5 kilocalories S-1 M2, A equals 0.02 M2, T equals 20 S. Q equals rad equals 0.5, 0.02, 20 equals 0.2 kilocalories. This is the required quantity. Exercises Q22, page 74. Compare the rates of emission of heat by a blackbody maintained at 727 degrees Celsius and at 227 degrees Celsius, if the black bodies are surrounded by an enclosure black at 27 degrees Celsius. What would be the ratio of their rates of loss of heat? Solution. Exercises Q23, page 74. The Earth's mean temperature can be assumed to be 280 K. How will the curve of blackbody radiation look like for this temperature? Find out lambda max. In which part of the electromagnetic spectrum does this value lie? Take B equals 2.897 times 10 to 3 mK. Solution. This value lies in the infrared region of the electromagnetic spectrum. The nature of the curve of blackbody radiation will be the same, but the maximum will occur at 1.035 times 10 to 5 m. Exercises Q24, page 74. A small black and solid copper sphere of radius 2.5 centimeters is placed in an evacuated chamber. The temperature of the chamber is maintained at 100 degrees Celsius. At what rate must energy be supplied to the copper sphere to maintain its temperature at 110 degrees Celsius? Take Stefan's constant sigma to be 5.67 times 10 to 8 JS1 M2K4, and treat the sphere as a blackbody. Solution. Data. R equals 2.5 centimeters equals 2.5 times 10 to 2 m. T0 equals 273 plus 100 equals 373 K. T equals 273 plus 110 equals 383 K. Sigma equals 5.67 times 10 to 8 JS1 M2K4. The rate at which energy must be supplied equals. Exercises Q25, page 74. Find the temperature of a blackbody if its spectrum has a peak at A. Lambda max equals 700 nanometers, visible B. Lambda max equals 3 centimeters, microwave region C. Lambda max equals 3 centimeters, FM radio waves. Take Wien's constant B equals 2.897 times 10 minus 3 meters. K. Solution.